Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 10 from the May-June 2023 Cambridge 9709 Pure Mathematics Paper 1 Variant 1. This question here is about volumes of revolution, and it's a particular case of it which is very important for us to understand, and many people do have some misunderstanding of this topic. So we have here a part of a curve with equation y equals 4 over 2x minus 1 squared, and parts of the lines x equals 1 and y equals 1. The curve passes through the points A, which has coordinates 1, 4, and B, which have coordinates 3 over 2, 1. Find the exact volume generated when the shaded region is rotated through 60 degrees about the x-axis. Now, this question is a bit different. Why? Because normally what we're used to seeing in the past is, or are questions like where the whole of this region would be shaded. Okay, so the whole of the area under the curve would be shaded, the whole thing here, and it would simply be a case of taking this section here and applying the rule of volume of revolution about it. But here there's a gap in between. So first of all, what does it mean by the volume generated when it's rotated 360 degrees about the x-axis? What does it actually mean? Okay, so I'm going to just illustrate that to you, hopefully, by using this over here. What I'll do is I'll just take this, I'll copy it, and I'll paste it, and I will flip it upside down. Can I do that here? Yes, I can. Up, down. All right, so I'm going to put it like this. I'm going to make it a bit transparent so that we can see what's underneath. Okay, so yeah, just put it exactly over it. So basically, when this is rotated 360 degrees about the x-axis, basically what's going to happen is you're going to form a shape which is going to change the color, which is going to basically, it's going to come out of the page and go back into the page, this whole shaded region. So you'll end up with something like that looks, if you try and make this three-dimensional, like a ring. Just moving it down. Looks like a kind of ring. Okay. And it will be kind of like this. Now, if it was such that it was, so it's going to make this kind of shape. If it was such that it was shaded all the way down to the bottom, then this would be like a solid ring all the way through. But because there's this gap in the middle, all right, this part is not going to be included. There's going to be like a hole in the middle of it. There's going to be a hole in the middle from the front to the back. So if you look at it like straight on, okay, if you look at it from this angle over here, you'll see something with a hole in it like this. Okay, so imagine we just choose a small thin slice of like a cylinder right at the beginning or anywhere through the section. We take like a cross section, okay, and we consider that cross section. So you have a small thin little cylinder, okay, which we're kind of going into the page. So you have basically, if you want to find the volume of the cylinder, you would have to find the volume of the whole thing and take away the volume of the small part. So let's call this big R, the radius of, the big cylinder, and then we take the radius of like the hole in the middle as small r. So as we know that the volume of a cylinder is pi r squared h, so the volume of this shape will be, now we have to find the volume of the whole thing. So it's going to be pi times capital R squared h, which is, h is going to be how thick the cylinder is, okay, minus pi times small r squared h. So you can think of this as pi, you can say times h times capital R squared minus small r squared. Okay, that h is the same for both of them. So that would be the volume of the shape with the bit in the middle missing, with this bit in the middle missing. Okay, so if I find the sum of all the volumes of all the cylinders from where we're starting, which is 1, to where we're finishing, which is 3/2, I find the sum of all those volumes, I'll get the volume of this whole shape. So now let's relate to here what the radius is of this cylinder. Okay, if you think about the outer cylinder, the radius is basically the y value up here, the y value of this function here. Okay, so it's the y value of this function. Okay, so let's call that y1. Okay, let's call that function y1. And the small r would be the y value of this function. Let's call this line y equals 1. So let's call that y2. So basically what we would have is the volume is going to be pi times, let's leave with the h later on. We'll have pi times, we're going to have y1 squared minus y2 squared times how high or how thick this cylinder is. So we're going to take a small, tiny little slice of cylinder. So we're going to call that thickness dx. So this is going to be a small amount in the x-axis. Okay, so pi times y squared minus y squared. So the radius of you can say the y value of the one that's higher up, of the curve that's higher up, minus the y value of the one that's lower down. Okay, but you square them first. So y1 squared minus y2 squared with respect to x. Okay, that will give you the volume of this shape. Okay, if I basically take limits between the start and the end point, in this case, that's going to be x equals 1 to x equals 3/2. And I find that will tell me the sum of all the volumes of all those kind of cylinders with holes in them all the way between there and there, and it will give me the volume that I need. That's one way of doing it. That's the way I'm going to show you. There's also another way we can do it, where we can find the volume of this cylinder. So we can find the volume of the whole thing by just taking the integral of this function, okay, squared with respect to x, take away the volume of this cylinder. We can actually work out the volume of the cylinder because it's like just a horizontal line. So it's going to give you, pi times r, which would be 1 squared times, this will be between 1 and 3/2, okay, which is going to be 0.5. That will be the height. You can find the volume of that cylinder, take it away from the volume, but this method here I think will work well because it works when you don't, even when you have another function between two functions, it works. So you should understand this because it might not always be horizontal lines that you have here. It might be other things which this makes life, then, you have to know how to do this. So this is good for us to understand how to deal with. Okay, so I hope that was clear how I'm going to go about this. I'm going to get rid of this diagram now and this writing, and I'm going to just answer the question. Okay, so let's just get rid of all of this for now. And now, so hopefully you understand exactly why I'm going to do what I'm going to do. So I know the volume of the revolution I'm trying to find is equal to pi. I like to write the pi outside. You don't have to. Times between the limits of 1 and 1.5. Put 1 and 3/2 of, we're going to have, this is going to be 4/2x minus 1 squared, all squared, minus, and you're going to have the y value, this is y equals 1, minus 1 squared, okay, and that is going to be integrated with respect to x. And that will give us the volume of this as we rotate it around the x-axis. So now let's work out what we're going to get. We're going to have pi times between 3/2 and 1. If we square this, you're going to get 16 over 2x minus 1 to the power of 4 minus 1. We're going to integrate that with respect to x. So to prepare this expression for integration, I'll write this as 16 times 2x minus 1 to the power of negative 4 minus 1 Now we're ready to start integrating. It's 1, and that's 3 over 2. Okay, so when we integrate something like this, okay, we can see we can do this by reversing the chain rule, because outside the function is something of the form of the differential of what's inside the function. Okay, you differentiate 2x minus 1, you get a constant. There's a constant outside it. That's fine. So we have v equals, so when I integrate it now, I'm going to have 16 times 2x minus 1 to the power of minus 3 over minus 3 times 2. Okay, and then minus x. And then I'm going to have the limits 3 over 2 and 1. Okay, so now I have integrated this. Let me simplify it before I put the values in. So don't forget the pi. Don't forget the pi. Very important. Okay, if you forget the pi, you're going to have problems. Don't forget the pi. Don't forget the pi. So you're going to have 16 over minus 6, and it's going to be negative. So negative, that's going to be 8 over 3 times 2x. In fact, I can write this underneath as well. That will make life easier. So minus 8. So I have minus 8 over, you're going to have the 16 over 6, sorry. 16 over 6 is going to be 8 over 3 over 3 times 2x minus 1 cubed minus x. And I'm going to have my limits 3 over 2 and 1. So that's pi times, now I can put I'll put it down here because I might have space a bit. Do I have space on the next page? Not really. Okay, I take up a bit too much space here, but anyway, let's do this here then. So you have pi times, I'm going to have minus 8 over 3 times 2 times 3 over 2. That's going to give me 3. 3 minus 1 is 2. That's 3 times 2 cubed. Okay, minus, then I'm going to have a minus again here. I'm going to put 1 in here, so I'll have 8 over, sorry, I forgot the minus. My bad here. I've got minus x, so I've got minus 3 over 2, minus, and then I'm going to have minus 8 over 3 times, I'm going to put 1 in here now, so I have 2 minus 1, which is 1, 1 cubed, minus 1. Okay, so this should give us our answer. So that's going to be 8 over 8, which is 1, so minus 1/3. So pi times minus 1/3 minus 3 over 2. And this is going to give me minus 8 over 3, plus 8 over 3, plus 8 over 3, and plus 1. Okay, so what does this give us? That's minus 1/3. Okay, plus 1, that's going to be 2/3. So that's that's going to be pi times, don't forget the pi. Pi times, you're going to have 2/3, and that's going to be plus 5 over 3. No. Sorry. Different denominators here. I thought that was over 3. So that's going to be, okay, so you have 2/3. I'll do this one go. I'm going to have, this is going to be 1 minus 1/3 is 2/3 plus 8/3, that's 10/3, so 10 over 3, and minus 3 over 2. Minus 3 over 2. So this gives me over 6. That's going to be 20 over 6. So you're going to have pi times 20 over 6 minus something over 6. That's going to be times 3 times 3, 9 over 6. Okay, so you have 11 pi over 6 cubic units. So there is the volume. Okay, I took up a bit too much space there, but that's the volume of revolution, and it tells us to find the exact volume. Okay, the exact volume. Okay, so that's why, you work out the exact fraction, leave it in terms of pi, and that's the answer to this question. Okay, so you got to understand this whole thing about when you find the volume of a ring kind of type of cylinder, it's going to be pi times the big radius squared minus small radius squared times the height. Okay, you don't just subtract the radiuses, you subtract the square of the radiuses, okay, to give you the volume of the shape like this. It's very, very important for us to understand. So I hope that was clear. Other questions? I'm going to do part B actually. Okay, so I'm going to do part B actually in a separate video because it's more to do with differentiation, right? So I'm going to deal with that in a separate video, and so that will be separate from part A. Okay, so you'll find them both in the playlist over here, which is for this paper, and you'll find the other this video in or you'll find the playlist for the topic that this is from, where you see other questions of this type of volumes, or well, basically integration. Okay, in this playlist over here, and you can find other questions about volumes of revolution. I'll make a separate playlist for that, which will be over here. You can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.